Hello dear students, once again welcome back to the class. This is a very fresh morning and we are here to start a new topic, that is photoelectric effect and the wave theory of light. You have learned about the photoelectric effect and now in this lecture we will be learning about the wave theory of light. Let me first of all recall what we have covered in the last class. I have left the class with the graph that I have drawn. I must show you that graph. The graph was plotted between the stopping potential and the frequency of incident radiation. Frequency of incident radiation. We have seen that the graph between, I am writing the stopping potential as V0 because we denote the stopping potential as V0. So if we are plotting this graph, we have seen that for the two metals, the graph was something like this. It's a straight line. Say this is metal A and this is metal B. So what did we see in this graph? We saw that this is the axis that is representing the frequency. So this is nu naught 1 and this is nu naught 2. These nu naught 1 and nu naught 2 are the threshold frequency. I don't remember if I have introduced the term threshold frequency before you or not. So we have learnt about the threshold frequency. This is that minimum frequency below which there will be no emission of photoelectrons. And this is the stopping potential. This is V01 and this is V02. Or I can say that this is not the V01 and V02, this is phi 01 by E and this is phi 02 by E. This phi 0 is represented for the work function. Now let me just tell you one thing. After drawing this graph, we have discussed some discussions, we have discussed some conclusions that this phi naught E, I have told you that we will be discussing this phi naught, why this phi naught is coming in detail in this lecture. So we will be continuing with that. Here in this graph you can see this is nu naught 1 and nu naught 2. If your frequency, that means the frequency of incident radiation will be lesser than this incident than the threshold frequency, then there will be no emission of electrons. And when there will be no emission of electron, that means no photoelectric effect is being occurred over there. Okay. So now we are going to discuss first of all what are the laws of photoelectric emission. So laws of photoelectric effect, emission. Now I want to tell you one thing, that we are going to discuss this wave theory of light just in a minute, but before that you should be knowing that what are the laws of photoelectric effect. So first law of photoelectric effect is that the photoelectric emission is an instantaneous process. What do we mean by the instantaneous process? That means the moment electron is being the moment radiation is being falling upon the photosensitive plates, with no time lag the electron will be starting emitting from the sensitive plate. So that means photoelectric effect is an instantaneous process. First of all, now secondly, the second law says that until and unless your frequency will be greater than this threshold frequency, let me just denote and write over here, this is the threshold frequency. If the frequency of incident radiation is less than the threshold frequency. If frequency is less than the threshold frequency, so there will be no emission of electron. Or I can just say in another manner that if the frequency of incident radiation is greater than the threshold frequency, only then the photoelectric emission will take place. So I think I should write in positive manner that if frequency of incident radiation is greater than threshold frequency, only then photoelectric emission will take place. And change the sign as well. If nu is greater than nu naught, then only emission of electron will take place, otherwise not. You can note down these laws of photoelectric emission because this is an important thing that you should remember. Now if I talk about the third law, this third law says that the intensity of the photoelectrons, or I can say the intensity is being dependent upon what? I have told you that the number of photoelectrons emitted per second from the surface of metal is dependent upon what? Is dependent upon the intensity of the incident radiation. Intensity of incident radiation, and it is independent of the frequency of incident radiation. Now, here we have talked about the number of photoelectrons. The fourth law says that the kinetic energy with which these electrons are being emitting out, that is dependent upon the frequency of the incident light, and it is independent of the intensity. It is dependent upon the frequency of light and independent of the frequency. While this case is just opposite of that, here the number of photoelectron emitting is dependent upon the intensity and it is independent of the frequency of incident radiation. So, can I write over here? Will it be visible to you if I will be writing over here? So, the maximum kinetic energy of the photoelectrons depends upon the frequency of incident radiation. Okay. So, these are the four laws that you should not forget. You should not forget at all. I am repeating. This should be in your mind whenever you are dealing with this chapter. Okay. So, these are four laws. You can take a note of this so that now I am moving on to the topic of the session, that is wave theory of light. If I talk that we have seen the wave nature of light, then you will be saying that yes, the light is obeying the wave nature, it always shows the wave nature. Because in the chapter optics you have learnt the topic interference, diffraction, polarization, reflection, refraction and so many things. That are the options, that are the things which is showing, which is being satisfied with the wave nature of light. But here in this effect, that is photoelectric effect, if I talk about the photoelectric effect, there will be no obey of the wave nature of light. For example, if I will be telling you one by one, we will be watching that these laws, these four laws are not being followed by the wave nature of light. How? You will say how? Let me just start. if light is of wave nature, then suppose I am giving you an example. This is a metallic surface. Okay. Light is being falling upon this metallic surface. Light is being falling upon. What is the photoelectric effect? When light will fall upon, electrons will be emitting out. These are radiations and these are the electrons. This is what? This is photoelectric effect. Now what next? If light is of wave nature, that means all the waves should be coming and should spread over the surface of the metal like this. That means all energy should be absorbed by all the electrons that is present over the metallic surface, over the surface of metal. And if the energy is being absorbed by the electrons that is present over the surface, then what will happen? Here in the photoelectric effect, we see that with no time lag, all the electrons start emitting. But if light is of wave nature and the light is falling over the surface, the energy is being absorbed by all the electron. So that means if I talk about one single electron, that will be getting very much less energy, isn't it? Because now the energy is being transferred to all the electrons. Earlier in the photoelectric effect, we were saying that one photon or the one radiation is being absorbed by one electron. But here all the radiation are being transferred over the surface, so that means it is being transferred, it is being shared, energy is being shared by all the electrons. When the energy is being shared, that means only one electron will be getting lesser energy, and this energy will be very much less to emit out from the surface of the metal or to jump out from the surface of metal. So that means this energy is very much small. Together, that much energy which is required to emit out of the metallic surface, this need around 1 month or 2 months or number of days. So that means to getting the threshold frequency, the energy which will be equal to the work function of the metal, or the frequency which is greater than the threshold frequency, to gather that much energy, it will be requiring number of days or number of months. So that means you cannot say that photoelectric effect is an instantaneous process. It means it will be taking number of days. So that means your first law, that is photoelectric effect is an instantaneous process, that is not getting followed by the wave nature of light, right? You have seen that this is being declined, that this is not an instantaneous process, it will take number of days or number of months. So we can say first law is denied. What is the first law? That it cannot explain that photoelectric effect is an instantaneous process. The second thing is that when the electrons are being falling upon, the radiation is being falling upon, so we can say that number of frequency are being falling upon the surface, and no matter whatever be the frequency, your electron should be emitting out. But in the case of photoelectric effect, this is not possible at all. To get the electron being emitted out, this condition should get fulfilled. Otherwise, there will be no emission of electron. But in this case, that means if wave nature, if we are talking about the wave nature, we can say if the waves are falling over the metallic surface, so that means whatever is the frequency of the incident radiation, your electron should emit out. But this cannot happen in the case of photoelectric effect. It can only happen if your frequency is greater than the threshold frequency. So that means it cannot explain the concept of the existence of threshold frequency. So secondly, we can say we are talking about the wave nature of light. So that means this wave nature cannot explain the existence of threshold frequency. Now, if I move to the third point, we see that here in this case, we say number of photoelectrons emitting per second from the surface of metal is dependent upon the intensity of light. But here we see that number of electrons, number of radiation that will be falling will be dependent upon the number of photoelectrons that will be emitting. Will it be dependent upon the intensity of light or not? Because according to this principle, photoelectric effect, it is dependent upon the intensity. But here we say that more the number of radiation, more will be the, you can say, number of electrons that will be emitting. And yeah, third point we can also consider in terms of, if we are talking about the maximum kinetic energy, that kinetic energy of the radiation of the electron will not be dependent upon the frequency, but it will be dependent upon the intensity. How we can say this is more this is having more energetic, this electron is more energetic, or this is having maximum kinetic energy? Here, because the waves are being falling upon the metallic surface, so when the energy will be absorbed by the electrons that are present over the surface, more the energy gained, more will be the velocity of electron. What did I said? More the energy absorbed, more will be the velocity of electron. So that means it is dependent upon the intensity. But it is just contradictory of this case, that means maximum kinetic energy of photoelectron is being dependent upon the frequency and it is independent of the intensity. So it cannot explain that maximum kinetic energy of electrons, emitted electrons, depends upon it cannot explain that the maximum kinetic energy of the emitted photoelectrons depend upon the frequency. Because it was saying more the intensity, more will be the ejection of the electrons, emission of the electron, right? So that means if these are not being obeyed, we cannot say that light is being shown, light is showing the wave nature. Here, after watching over these things, we can say light is not showing the wave nature, but light is showing the particle nature. So the chapter name was dual nature of radiation and the matter. So we are talking about radiation, we have seen the wave nature of radiation. Here we can say because light is not showing the wave nature, so that means light is showing the particle nature. And the Einstein, the very brilliant scientist Einstein, he has then concluded that if the light is not showing the wave nature, that means light is showing the particle nature. That means the light, the radiations, they are formed by small packets, and these packets were called as the quanta. The quanta then can be together called as the photon. What did we said? We said that the light is composed of photons. So we will be writing over here, I am removing this laws of photoelectric effect. Okay. So what did Einstein say? That Einstein concluded light is composed of photons. Light is, and this was a very important conclusion because it has concluded that light is showing another nature as well. Light is having dual nature. So light is composed of photons. These are small packets of energy. Okay. Now, so that means when the radiation is interacting with the matter, because in this example you can say these are the radiation, this is the metallic surface. So radiation is interacting with the matter. Matter is what? In the very beginning I have told you matter is something that is having mass and that occupies space. So this is the metallic surface, it is having some mass and it occupies space, so we can call it matter. So now if the radiation is interacting with matter, it is showing the particle nature. So then he said that light is composed of particle which we call as the photons, and these photons have energy which is equals to h into nu, where h is your Planck's constant equals to Planck's constant and nu is the frequency of incident radiation. And he said that the light is light is composed of small particles which we call as photons. These photons will be having some energy and also it with associated momentum. So that means with this small packets, momentum and energy are associated. We have discussed about the energy. If we talk about the momentum, he said that momentum is okay. Before telling you about momentum, because this momentum we are going to discuss in the another section as well, where we will be discussing about the totally the particle nature of light. So there a relation came that when this light will be, I will be discussing about the momentum later on. Now I should tell you one more thing over here, and that thing is that the energy with which light is falling upon the surface of metal, half of the energy, or you can say one part of the energy, is being used up in emitting the metal from the metallic surface, emitting the electron from the metallic surface. So go back to the figure, we will be discussing it here. If the radiation is falling, it is having some energy, we say this as h nu. Now when this radiation are being falling, half of the energy will be used to emit the electron from the metallic surface. That means to overcome the work function. What is the work function? The minimum energy required to bring out the electron from the metallic surface. So half of the energy will be used up in, let me just write over here, this was the energy, that is h nu. One part of the energy is used in overcoming the work function, that is phi naught, and the energy which is remaining, total energy was h nu, it was falling upon the surface. Half energy is used in overcoming the work function. So the rest will be used in increasing the kinetic energy of the electron. So it is increasing the, or it is giving the kinetic energy of emitting electrons. Okay. So that means these energy we can represent in the equation form as h nu equals to phi naught plus the kinetic energy, that means half mv square max, because this is the maximum kinetic energy. So we are having this equation, and this equation was termed as the Einstein's equation, Einstein's photoelectric equation. This is the very important equation, because whether you are solving the question for JEE Main, you are solving the question for CBSE, for the NEET, for JEE Advanced, this equation will be very helpful to you, because the question from this chapter will be based on this sole equation. You can write this equation as, because if your frequency of the incident light is say nu naught, that means the threshold frequency. So at that time the energy associated with that particular photon will be h into nu naught. So you can say that your work function can be written as h into nu naught, or I should tell you in another form, phi naught is the work function. We define the work function as the minimum energy. So energy can be written as h into nu naught. Nu naught is the minimum frequency. That is how your phi naught is represented as h into nu naught. Now put this value phi naught over here, we will be having h nu equals to h nu naught plus half mv square. Now to find out the kinetic energy of the electron, we can represent the equation as half mv square equals to kinetic energy max, it is equals to h nu minus h nu naught. Now there are number of conclusions that we can draw from one particular equation. The conclusion that I can draw from this equation is that if my nu is less than nu naught, that means this was the second law of photoelectric emission. The photoelectrons will be only emitting out only and only when nu will be greater than nu naught. What did I said? I think I should write over here, this was the condition of the law, that if your frequency of the incident radiation is greater than the threshold frequency, then only the photoelectric emission will take place. Now in this case, if I say that my nu is less than nu naught, that means this kinetic energy will be coming out to be negative. So that is impossible. So that means to get the energy of the electrons to emit out, your nu should be greater than nu naught, and this we have verified by this equation. Now there is one more thing. There was a scientist named Millikan. He tried to you can say to overcome over the scientist Einstein. He was trying to disprove that this equation is not correct, this equation is wrong. He was trying to make the scientist Einstein fall down. So that he tried to do number of experiments, and while he was doing the experiment, he plotted the graph between stopping potential and frequency of incident radiation. Let me just draw that. When he plotted the graph between frequency and the stopping potential, on the y-axis he took the stopping potential, and on the x-axis he considered the frequency of incident radiation. Again, when he plotted the graph, he saw that this was a linear relation and this was coming out and reaching to this point, say phi naught by E. Now one more thing, he saw that we are having this equation half mv square equals to Ke max equal to h nu minus h nu naught. So let me just change the topic now. Here we are now discussing the verification of Einstein's photoelectric equation. Because by the experiment of Millikan scientist, this equation has been verified that this equation is correct. Einstein's photoelectric equation. Okay. So when he plotted the graph, he saw that Einstein has given this equation. He said that kinetic energy can be written as, if E is the charge of electron and V naught is the stopping potential, so kinetic energy of the electrons can be written as E into V naught, isn't it? So if we can represent the kinetic energy as E into V naught, so by putting this value over here, we will be having E into V naught equals to h nu minus h nu naught. Now because he has plotted the graph between V naught and nu, bring out the value of V naught from here, h nu by E minus h nu naught by E. Now on comparing this equation with y equals to mx plus c, this was plotted on the y axis, this was plotted on the x-axis. So this is y equals to mx plus c. So that means this particular value h by e is the slope. M is what? M is slope. So that means he has written the h by e. I have told you that I am writing phi naught over here, and I will explain why did this came. You can write this phi naught as h into nu naught. I told you right here, h into nu naught. And what is this? H by e. So this is nothing but, you can write it as h nu naught by e. Because don't write naught over here, you can simply write phi by e. So this is h nu by e, which is nothing but the slope. So when he said that after performing number of experiments, he had find out the slope from this equation, and by knowing the charge on the electron, that is 1.6 into 10 raised to the power minus 19, he had find out the value of h, that is Planck's constant. And from there the value has came out to be 6.6 into 10 raised to the power minus 34. So that means this value which is coming out after plotting this graph and verifying with this equation, this was coming into the agreement of the exact equation. So at that time he saw that I was trying to disprove the equation, but this equation is very much correct. So this Millikan experiment, this experiment has proved that this equation is totally correct. This is the correct equation of Einstein, which we can use to find out the velocity of emitted electrons, or we can use it to find the frequency of the emitted electron, so or the energy of the emitted electron. So after learning about this, I think we should wrap up this session, because in the next session again we will be continuing with the same discussion with the same topic. Till then, just take care. Thank you.